Just like many other areas of mathematics, there are some properties for definite integrals that you want to make sure that you know. The first property is that if you have the same bounds, so you take a definite integral from x equals a to x equals a, that integral is going to be 0. The reason is if you aren't going anywhere on your x-axis, you have no area. So there is no area, there is no definite integral if you go from x equals a to x equals a. Also, if your bounds are essentially backwards, so let's say that this is a and this is b, and you have a function like so. If you were to do your integral from b to a, that's like backwards on your number line. So we change that by doing the negative of this way. Think about maybe if you had like a value on this side and you were doing something with distance or total distance traveled, or something of that nature. It might make sense to set up your integral in a way that your bounds are backwards and then just realize that that would then be the negative of the area from a to b here. All right, if you end up having two functions, f of x and g of x, on the inside of your integrand, you can split those up. Same thing with subtraction, you can split those up. So if you needed to find the integral from 0 to 1 of, let's just go super easy here, x plus 1 dx, that would be the line x plus 1 from 0 to 1, and you could split this up into a rectangle area of 1 and a triangle area of 1/2, and get that this would be 3/2. You could split this up though into using one of these two properties, the integral from 0 to 1 of x dx plus the integral from 0 to 1 of 1 dx. When I do that, this area ends up being this piece here. This area ends up being this piece here. And so you end up getting the same area. Additionally, if you have a constant on the inside of your integrand, you can just take that constant out. So if I wanted to integrate, again, let's just go something simple, 0 to 1 of 3x dx. So 1, 3. That area is actually also 3 over 2. I didn't really mean to do that, but that triangle, 1/2 base times height, would give us 3/2 as our area. But that's the same thing as 3 times the integral from 0 to 1 of x dx. We said up here that integral area of 0 to 1 of the integral of 0 to 1 of x dx, excuse me, I got tongue-tied there, would be 1/2, like that piece is this piece here. And so if I multiply that by 3, I get the same thing. So it's okay to just pull constants out of your integrand. And then the last rule is if you end up having an integral from a to b and then c is between those values, then you can split this up. So if you have from a to b some function, it is okay to say, okay, take the integral from a to some value c, and then add that area to go from c to b. So area 1 plus area 2 would end up getting you the full area piece. That's the concept we're going to do here in this example. So let's say that I know the area between 0 and 8 of some function, between the function and the x-axis between 0 and 8. So this area is 10. Well, let's also say that I know that the area from 0 to 5 is 5. Well, then the only way I can get to a total of 10 is if the integral from 5 to 8 is also worth 5. Another example that we might want to look at, just using a couple of these other properties, is what if I wanted to find the integral from 0 to 5 of 2 f of x dx? Well, I can use the property that I can take the constant to the outside, and then I can take the integral from 0 to 5 of f of x dx. So that would be 2 times 5, which gives me 10. If there was a negative on the inside, that negative just pulls to the outside, negative here, negative 10. So anytime you have that constant multiple, most of the time we'll go ahead and take that out because it's just easier to evaluate that function without it in there.